Okay, so today we're going to get a little more practice with higher order derivatives. So it says find the first four derivatives of y equals 2x cubed. So y prime will just be 6x squared by our power rule. Y double prime is just the derivative of the first derivative. So that's going to be 12x. Y triple prime is going to be just 12. And then y the fourth derivative, remember on the fourth power we switched to writing it in parentheses there, is going to be the derivative of a constant is just 0. Okay, so let's take a look and see if we can figure out what's going on here. So the nth order derivative of f of x equals x to the n is a constant. Okay, so let's go back and look at that. So when this was degree 3 because the power on x was a 3. So the third derivative was a constant. Okay, we can see that. So all derivatives of order n plus 1 or higher equal 0. So if it's a degree 3 equation, the third derivative will get us to the constant. Everything after that is just going to be 0. Because if we took the fifth derivative, the derivative of 0 is still 0 because 0 is a constant just like 12 was a constant. And so we're going to stay at 0 for all higher order derivatives. See, we're thinking. Okay, now let's try another one. This one says, find the second derivative of the following. Okay, we've got a quotient rule. So first derivative is going to be derivative of the first times the second minus the first times the derivative of the second all over the second squared. Okay, so let's clean that up a little bit. That's going to look like x plus 2 minus x over x plus 2 quantity squared. X and negative x cancel each other out, so that just gives me 2 over x plus 2 quantity squared as our first derivative. Okay, so now we want to take the second derivative. So y double prime is going to be the derivative of that. Now, I don't want to take the derivative of it in that form because right now it's looking like a quotient rule, and I really don't want to do that if I don't have to, because I can just rewrite that with my algebraic properties, and that will be easier. Y prime can be rewritten as 2 times x plus 2 to the negative 2 power. And now it'll just be a chain rule, which will go much easier. Okay, so let's try that. So we're going to do y double prime now. So y double prime, because I wanted to change colors, okay, is going to be negative 4 times x plus 2 to the negative third power times the derivative of the inside, which is just 1. Okay. So if I want to go ahead and rewrite that, that is going to look like a negative 4 in the numerator. The x plus 2 is going to go to the denominator where its exponent will become positive. And that's our second derivative of that function. Okay, didn't that make that so much easier doing our chain rule like that? Okay, so remember you can rewrite those equations if you'd like. Let's try another one. Find the second derivative of the following. Okay, again, I'm going to rewrite this. The original function is just 4 times x to the 1/2 minus 6 times x to the negative 1/2. Okay, and let's go ahead and find, they want second derivative. So we've got to start with the first derivative. So the first derivative of that is going to be 1/2 times 4 is going to be 2x to the negative 1/2. Negative 6 times negative 1/2 is going to be positive 3x to the negative 3/2. Okay, and then I think actually I'll leave it in that form. All right, so now we're ready to take the second derivative. So let's go ahead and do that. So f double prime of x will just be negative 1/2 times 2 is going to be negative x to the negative 3/2. Negative 3 times 3/2 times 3 is going to be minus 9/2 x to the negative 5/2. Okay, now we can't, this is the form that they actually asked for. They asked for the second derivative, and so we do need to clean this up. We can't leave the negative exponents here. So let's see what this is going to be. So this is going to be negative 1 over x to the 3/2 for that first term, minus 9 over 2, that's the 9/2, x, because the exponent was negative, it's down in the denominator, to the 5/2. Okay, when I'm looking at that, I'm like, we could clean that up. So let's try cleaning that up. Let's try writing it with a common denominator. Our common denominator would need a 2, and it would need an x to the 5/2. So what do I need to multiply that first term by to get that common denominator? It needs a 2, and it needs an x to the first power, which is 2 over 2. X to the first power is just x to the 2/2. So I'm going to multiply the numerator and the denominator by 2x to the 2/2. Okay, so that's going to give me negative 2x, because 2 over 2 is just a power of 1, and if the exponent's 1, we don't have to write it. Okay, so when I multiply that, that's going to be negative 2x, minus the second term already was over that denominator, so it's just going to be negative 2x minus 9 over 2x to the 5/2. Now, that's not finished simplifying. Let's finish cleaning that up, because in that denominator 5/2, we've got stuff that we can pull out of that. That's going to be negative 2x minus 9 over, because that's x to the 5/2, that's x to the 2.5. So I can pull 2 of those x's out of the radical, and it just leaves a single x under the radical. Okay, so there we go. Final answer, cleaned up nice and pretty. That's my f double prime of x. Okay, let's try one last one. Find the second derivative of the following. Good, we get to practice some trig functions, so that'll be good. Let's go ahead and get started on that one. They want second derivative, so we're going to start with first derivative. So h prime of theta, derivative of sine is cosine, so that's going to be cosine theta, minus, this is just a sum and difference, because we've got terms joined by a minus sign, so that's a sum or difference. So it's just derivative of the first minus the derivative of the second. Now the second is a constant multiple, so that's going to be 3 times, so minus 3 times. The derivative of secant is secant tangent, so that's secant theta tangent theta. Okay, and that's our first derivative. Not too bad. Okay, that parentheses is optional there. You don't need that because it's just that. But when we go to take the second derivative, h double prime of theta, it's a big theta, okay, it's still going to be a sum or difference. We've got derivative of the first. The derivative of cosine theta is negative sine theta. And it's going to be minus 3 times, and this time we are going to need that parentheses. Okay, now this, inside the parentheses, secant theta, tangent theta, is a product. So we're going to have to use our product rule here. So let's go. Derivative of secant is secant tangent. So that's going to be secant theta, tangent theta. So that's derivative of the first times the second, which is a tangent theta, plus the first, which is secant theta, times the derivative of the second. The derivative of tangent is secant squared theta. Okay, so let's go ahead and distribute that negative 3 to our two terms there. So this is going to look like negative sine theta. And then we've got negative 3. This first term is a secant theta. And what is tangent theta times tangent theta? Tangent squared theta. I was going to put a plus, but we're distributing that negative 3. So I'm going to make that a minus 3. Secant theta times secant squared theta gives me 3 secants multiplied together, which we write as secant cubed theta. Okay, and there we go. Final answer. Looks good. By the way, I couldn't help myself. I did go look at my Pythagorean properties to see if I wanted to change this tangent squared. But it would have been like a 1 minus secant squared theta. And then when we distribute the negative 3 secant theta to it, it doesn't end up looking any more simplified per se. So I just left it right here. But in case you were thinking about it, we could consider it. There are equivalencies with our properties and identities. All right, now it's your turn. Give it a try. Let's see how you do.